Many times when conducting research, our purpose is to make inferences about the population. There are two types of statistical inferences. One type is the estimation of a confidence interval for a population mean based on the mean of a sample. The other type of statistical inference, which we will discuss in this presentation, consists of testing whether a sample mean is significantly different than a given value. In most cases, the given value is the population mean for that variable. Let's start with an example. We know that the population mean for IQ scores is 100. But let's say that we would like to see whether this is really true. To do this, we must select a large random sample and compute the mean IQ score for our group. Of course, it is very likely for our sample to have a mean that is slightly different than 100. So the next question would be, is the sample mean significantly different than 100? In statistics, we must be very careful when we use the term significantly different. In order to determine if two numbers are significantly different, we must conduct a statistical test to provide evidence. We cannot rely on our subjective interpretation. So, to be able to determine whether or not the difference between the two means is statistically significant, we must collect some statistical evidence. And this is done by conducting a test of statistical significance. The first step in conducting a test of statistical significance is to state the hypothesis. Logical reasoning tells us that it is much easier to demonstrate that a statement is not true than to demonstrate that a statement is true. This is because we have to find only one instance when a statement is not true, rather than having to demonstrate that a statement is true in every possible situation. For this reason, when conducting a test of statistical significance, we use what is called a null hypothesis. We use the term null because we assume that there is no difference between the two means, or we can say that the recorded difference is not significant. The notation that is typically used for the null hypothesis is HO, or actually H0, because O is the symbol for null. For our example, the null hypothesis is that the sample mean is equal to 100, or that there is no difference between the sample mean and the population mean. Now, of course that the sample mean will be somewhat different, but what we're stating here is that the recorded difference is not a significant one. If we demonstrate that this null hypothesis is false, then its opposite must be true. The opposite of a null hypothesis is called the alternative hypothesis. The notation used for the alternative hypothesis is HA. For our example, the alternative hypothesis is that the sample mean is significantly different than 100, or that there is a significant difference between the sample mean and the population mean of 100. Either one of these statements is correct. Let's say that we have some reason to believe that the sample mean will be higher than the population mean. In this case, we have a one-sided alternative hypothesis because we are only looking at one direction in which the mean may vary. If we suspect that the sample mean may be either lower or higher than 100, the alternative hypothesis would be two-sided because we're testing both directions in which the mean IQ may vary. But for now, let's just focus on the one-sided alternative. So, in conclusion, when conducting a test of statistical significance, we are trying to provide evidence to reject the null hypothesis. If the evidence is strong enough to reject the null hypothesis, then we can automatically accept the alternative hypothesis. Nevertheless, if the evidence is not strong enough, we must accept the null hypothesis and reject the alternative, or, as statisticians like to say, we fail to reject the null hypothesis. But we will talk more about how to do this on the next slides. Let's say that the mean IQ score for our sample is 108. What can we conclude about this sample of data? The sample mean is obviously different than the population mean, but is the difference between the two values statistically significant? Or can this difference be attributed to chance or sampling error? The first step that we have to take is to compute what is called the Test-Statistic. And you already know how to do this, because the Test-Statistic is nothing but the z-score for the sample mean. The only difference is that here we divide the population standard deviation by the square root of n, just like we do when we compute confidence intervals. So, to use the formula for the Test-Statistic, we must also know the population standard deviation for our variable, which for IQ is 16. And we must also know the sample size, which for this example is 16. Of course, this number is very small, and in a real research scenario, the sample should be larger. I chose 16 here just to ease the computation process so that we can focus on the reasoning behind this procedure. So if we replace these values in the z-score formula, we have 108 minus 100 divided by 16 divided by the square root of 16. This leads us to 8 divided by 4, which is 2. So the z-score for our sample mean is exactly 2 standard deviations above the population mean. After computing the Test-Statistic, the next step that we have to take is to find out the probability of obtaining this score when the null hypothesis is true. As we already know, the normal curve helps us determine the percentage of individuals in the population who are located within certain intervals above or below a certain score. To find out this information, all we have to do is to standardize our score, which would by computing z, or the Test-Statistic. The area to the left of z represents the percentage of individuals in the population who are located below the score. The area to the right of z represents the percentage of individuals in the population located above the score. These percentages can also be represented or interpreted in terms of probability. So the area to the left of z shows us the probability of having a score lower than z if the null hypothesis is true. For hypothesis testing, however, we're interested in the area to the right of z, and this area is also called the p-value. The p-value represents the probability of obtaining scores that are at the z level or higher when the null hypothesis is true. Therefore, if z is far away from the mean, the p-value is small. The larger the Test-Statistic, the smaller the p-value. When the p-value is very small, we say that we have strong evidence that the null hypothesis is not true. This is because if the mean is the one specified in the null hypothesis, the probability of obtaining a score that is so extreme is very small. Your next question may be, okay, but how can we find out the probability for our Test-Statistic, or the z-score that we have just computed? Table A in your textbook provides the area to the left for every possible z-score. The rows of this table represent the first 2 digits of the z-score, and the columns represent the last 2 digits of the z-score. The z-score in our example was exactly 2, so all the decimals were 0. The area to the left for this z-score was 0.9772. But for hypothesis testing, we're interested in the area to the right of z, the p-value. Knowing that the entire area under the curve is equal to 1, we can obtain the p-value simply by subtracting the area to the left from 1. In our example, if we make this subtraction, we obtain the value 0.228. But how do we interpret this value? Well, we say that if the null hypothesis is true, that is, if the IQ population mean is equal to 100, there is only a 2% probability of obtaining a sample mean equal to 108. As I mentioned earlier, the smaller the p-value, the stronger the evidence for rejecting the null hypothesis. The question that you may now ask is, how small should the p-value be to be statistically significant? Is there a cutoff for the p-value? Yes, there is a cutoff for the p-value, and this cutoff is called alpha, or the significance level. The value of alpha is established by the researcher before even beginning the statistical analysis. In social sciences, alpha is typically set at 0.05 or 5%. This represents the amount of acceptable error, or the probability of rejecting a null hypothesis that is in fact true. It is also called the probability of type 1 error. To decide whether we should reject or accept the null hypothesis, we must answer a very simple question. Is the p-value for our z-score smaller or larger than alpha? If the p-value is larger than alpha, then we accept the null hypothesis and, of course, reject its alternative. If the p-value is smaller than alpha, then we reject the hypothesis and we accept the alternative hypothesis. For our example, the p-value of approximately 0.02 is smaller than 0.05, so our decision should be to reject the null hypothesis. Our test of significance showed that the difference between the sample mean and the population mean is statistically significant. A two-sided alternative hypothesis is used when we have no reason to believe that the sample mean can only be higher or only smaller than a given value. For our example, the alternative hypothesis was one-sided, so we only had to look at the probability that the sample mean was larger than 100. However, when the alternative hypothesis is two-sided, the sample mean can be both higher or lower than the given value. So we must look at both extremely low or extremely high values. So alpha is located at both ends of the curve. Half of alpha is located at the higher end, and the other half is located at the lower end. So there is both a low cutoff value and a high cutoff value. Therefore, in such situations, the p-value is obtained by multiplying the area to the right of z by 2. And only after multiplying this value we can compare the p-value to alpha. For example, the area to the right of z was 0.0228. So if the alternative hypothesis were two-sided, the p-value would be 0.0456. After we made this multiplication, the decision process is the same. If the p-value is smaller than alpha, we reject the null hypothesis. If the p-value is larger than alpha, we accept the null hypothesis. In this case, because 0.04 is still smaller than 0.05, we still reject the null hypothesis and we accept the alternative hypothesis. The p-value for a certain z statistic can be obtained from different places. You can use Table A in your textbook. Statistical software also provides the p-value for certain types of analysis, or we can use a calculator. Such calculators are available online. This is the link to such a website where you can input the value of z and the two-sided p-value is provided. Of course, if you need only the one-sided probability, then all you have to do is just to divide this value by 2. In conclusion, There are only 4 major steps that we have to take when we're conducting a test of statistical significance. First, we must formulate the null hypothesis and the alternative hypothesis. Second, we compute the test statistic, which for this type of test is a z-score. Third, we find a p-value for the test statistic from Table A. If the alternative hypothesis is two-sided, then we multiply the area to the right of z by 2. And fourth, we compare the p-value with the significance level, with alpha, and we decide whether we should accept or reject the null hypothesis. One thing that you must keep in mind, though, is that the z-statistic is computed based on the properties of the normal distribution, so it should only be used when the distribution of the variable is close to normal. If this condition is not met, a different statistic must be used.